Hello, this is Dr. Henry, and today we are going to be looking at periodic trends. Now, a periodic trend is anything that you can predict about an element based upon its position in the periodic table. And I have some example here of some other trends. So this would be like fashion trends, like wearing a shirt or sweater as pants. And I'm not sure exactly what this guy is doing right here, but he looks kind of angry. And this is a little old, so it didn't really look like anything that people dress nowadays. Maybe the 80s, but that's not really important. Let's get back to the periodic table. So the first trend we're going to talk about is atomic radius. And atomic radius is determined by basically measuring the distance between the center of two adjacent atoms, and then you just divide it in two to get the radius. But for us, really, all we want to think about is this right here, all right? So atomic radius is the distance from the center of the nucleus to the valence electron energy level. So from the center of the nucleus to the outside edge of the electron cloud. And we're going to look at what are the periodic trends in atomic radius. And the other thing is sometimes with atomic radius, we'll say size when we really mean radius. Because the greater the radius gets, the larger the atom gets. So for atomic radius, as you move down a group, atomic radius increases. Now, why does it increase as you move down a group? Well, it increases because the number of energy levels increases as the period numbers increase down a group. And I should have had a periodic table on that one too, but let's just say. So let's just say basically you had group 1, right? So here's group 1, there's 7 of them, there's hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. So, this is in the first period, second, third, fourth, fifth, sixth, seventh. So, hydrogen has one energy level. Lithium has 2 energy levels. Sodium has 3. So basically, as you move down, you're adding another level of electrons to those, and atomic radius is increasing. All right, let's look at the trend for left to right across a period. So we mean like if you start out at lithium and you go across this period, what happens to atomic radius? Well, we said when you go down, the number of energy levels increase. But here, everything in the second period has 2 energy levels. So that's not going to be the reason. And it turns out that atomic radius decreases as you move left to right across a period. And what happens is you are adding electrons to the same energy level. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, all of these in this second period, all of them have 2 energy levels. But what you're doing is, as you're adding more electrons, because atomic number goes up as you go across, so you're adding more electrons, but you're also adding more protons. And that increases the force of attraction, and that pulls the electrons closer to the nucleus. All right, and this should say, that shouldn't say atoms, that should say nucleus. So that's something I need to correct. So this is the reason why atomic radius decreases as you move left to right across a period. Because the force of attraction increases as you add more protons, it pulls the electrons closer, and that makes the atom smaller. Ha. All right, and if we look at this, we can see this. So basically, as You go down any of these groups, atomic radius increases. As you go across, atomic radius decreases. Now, you're going to see a couple exceptions to these rules, but we're just interested in these general rules and how they work. All right, so let's do a question. So circle the element with the largest atomic radius. So we have sodium, chlorine, and aluminum right here. So let's look at these. So these are all in the same period. And the trend is, as you go across a period, atomic radius decreases. Now, we want the one with the largest atomic radius. So chlorine is the smallest because it's furthest across, then aluminum, and then sodium. So sodium is actually the largest because aluminum and chlorine are further to the right. So our answer for this is going to be sodium. Now the question is why? So let's look at sodium. Sodium has an atomic number of 23. It's got atomic number of 11. It's got an atomic number of 23. Aluminum has a mass number of 27, atomic number of 14, and chlorine is 35 and 17. So let's look here. And I think I did this wrong. What's the atomic number for sodium? I'm getting old. I can't see as well as I used to. Yeah, I was right. So look. Sodium has 12 protons, aluminum has 13 protons, and chlorine has 18 protons. How many energy levels do all these have? Well, they're all in the third period, so they all have 3 energy levels. So these are the basic facts that we know about these. This is what we have to use. So if they all have 3 energy levels, which one of these is going to have the greatest force of attraction? Well, it's going to be chlorine because it has more protons. And the more protons you have, the greater the force of attraction between the nucleus and the outermost electrons. So, here's going to be our scientific explanation. So, sodium, aluminum, all right, sorry about that. A couple things were happening off screen I got to fix. So, and I also made a mistake because if you look down here, look, I circled chlorine because chlorine is the smallest. But you need to be careful because we're not looking for the smallest. What are we looking for? We're looking for the largest. So sodium is actually the largest. And here's our scientific explanation. So sodium, aluminum, chlorine all have 3 energy levels. But, and if you look here, look at this. I made another mistake. I'm just full of mistakes. Sodium has 12 protons versus 13 protons for aluminum and 17 protons. 17? I'm fired. 18 protons for chlorine. So since sodium has the smallest number of protons, its valence electrons have the weakest attraction to the nucleus, so it's larger than the others. So that's our explanation for why sodium is largest. To figure it out, you have to use this trend that across a period, atomic radius decreases. All right, circle the element with the smallest atomic radius. Hopefully this slide's a little better than the last one. So we're looking at cesium here, lithium, and potassium. So what do we know about these? They're in the same group. Lithium is in period 2. So lithium has 2 energy levels. Potassium is in period 4, so it's got 4 energy levels. And then cesium is in period 6, so it's got 6 energy levels. And we know as you go down a group, atomic radius increases. So, which of these is going to be the smallest? Well, lithium only has 2 energy levels, so it's going to be the smallest. And let's see if that's correct. Yep, lithium is the smallest. So here's our scientific explanation. So they're all in the same group. Lithium is the smallest because it has 2 energy levels versus 4 energy levels for potassium and 6 energy levels for cesium. All right, we got one more here, I think. So circle the element with the largest atomic radius. So we're looking at carbon, and I'm circling these just so we know where they are in the periodic table. Barium and zinc. Where's zinc hiding? There's zirconium. All right, there is zinc. So let's look at this. Now, these aren't in the same periods or groups, but we can look at this and we see, remember, so it decreases across and it increases down. So just looking at this, right, they get smaller as you go this way and they get larger as you go down. So we know that barium has to be the largest because it is the furthest down and it is the furthest to the left. So barium's going to be our answer. We know that barium has the largest. So the question is why? Well, the dominant factor here is going to be that barium has 6 energy levels versus zinc, right, which has 4 energy levels, and then carbon, which has 2 energy levels. So